All right, we're continuing the notes. We're on page 16 in our notebook. Okay, on section 3.5, and the 3.5 refers to like the section in our textbook. So that's what we're going through. Okay, and this is on how friction affects motion. And so you can kind of read through the blurb up here on your own. Basically, it's just saying like we have a 45 kilogram box, and depending on like the different scenario, there's going to be different forces applied to it, and we're going to be discussing that. And so this first example, we have this 45 kilogram box. Okay, there's no horizontal force applied, no motion is occurring, so nobody's pushing on it, it's just sitting there. Okay. A free body diagram would show a net or zero net force as the box is stationary, so it remains at rest. So again, if we were drawing a free body diagram, like we draw our weight in the middle, and then our weight would be coming down, and the floor would be pushing up with our normal force equal and opposite. Okay, now we have a 50 newtons applied. So someone's pushing against this with 50 newtons, okay, but no motion is occurring, which means that because it's not moving, there's a force pushing back with equal and opposite. And so again, like the force that we call that's pushing back is what we call static friction. Static means it's not moving, and the friction is a friction force. So that's where, like, if you're pushing something heavy, you have to overcome this force of static friction in order to actually get to move. And so if we increase the force to 75 newtons, the box still does not move because we haven't overcome the static force. So it's pushing back equal and opposite, and until you kind of overcome that force. So yeah, generally static friction is not a constant value. It increases as the applied force increases up to a point. So we'll talk about that point on the next page. So this is now page 17. And so again, increasing the amount applied, so 100 newtons. Okay, there's still 100 newtons pushing back. This box is still not moving. Okay, we have equal forces. Okay, but here we have 101 newtons, so just above 100, all of a sudden the box starts moving. So this is the acceleration because we have an F net, okay, and we have a mass. Okay, so mass times acceleration will give us our F net. Okay, so we still have 100 newtons of static force working back against it. Okay, and so we have to, so that's where we'd find our F net would be 100 minus our 100 newtons that are working in the opposite direction. Okay, and so because of this, so the maximum force of static friction is a bit more than 100 newtons. There's now a net force to the right of 1 newton acting on the 45 kilogram box. The acceleration predicted from Newton's second law, which is F equals ma, should be about 0.0222 meters per second squared to the right as observed. And so as you overcome the force of static friction, so the maximum force of static friction would be this 100 newtons. As soon as you apply more than 100 newtons, the box will actually start to move. The applied force is then increased to 130 newtons. The box accelerates faster at 1.5 meters per second to the right. And so that's what's shown here. So we're applying 130 newtons. The box is moving. Okay, but if you notice here, like our static friction is 100 newtons. Okay, down here, our kinetic friction, again, kinetic is the movement. Okay, kinetic energy is movement energy, anything like that. Okay, so we have 62.5 newtons of kinetic friction force, okay, which basically is saying that like the friction force actually decreases when the box is moving. So if the friction force is still 100 newtons, the net force would be just 30 newtons, okay, to the right. From Newton's second law, this should result in an acceleration of 0.667. But because we have a greater acceleration, this means that the kinetic friction, which occurs for objects sliding against one another, is less than the static friction. using the measured acceleration indicates a net force of 67.5 newtons is actually acting on this box. Okay, and we got that again, 45 times our acceleration, which means now that the kinetic friction, which we show here is 62.5, is less. Okay, and so just once you get the box moving, it actually takes less force to continue it moving because kinetic friction is less than the static friction that we need to overcome originally. A second identical box is placed on top of the first box. An applied force of 202 newtons is needed to accelerate the box initially. For an acceleration of both boxes of 1.5 meters per second, a force of 260 newtons must be applied. Okay, to accelerate the two boxes of total mass of 90 kilograms at 1.5 requires a net force of 135 newtons. Okay, if applied to the force is 260, therefore now our 260 minus our 135, so we get 125 newtons is the force pushing back. Basically what we're doing at everything, all of these numbers are just doubling as far as force to get the same acceleration. Because we have double the mass, we need double the force. And it'd be double the kinetic friction pushing back on it. Okay, so we're going to use these observations, okay, to help us with the first 5 questions in exercise 3.5, which is on the next page. So, exercise 3.5 on page 18. Okay, we'll go through some of these questions. I'm not going to write it all out, but you can write it in as I talk about it. Okay, does an object at rest on a horizontal surface necessarily have a friction force? Does any object have a friction force until a second force is added? So an object at rest doesn't really have a friction force because you need a force applied to have a force pushing back as a friction force. So that's, does any object have a friction force until a second force is applied? Really, they don't, because the friction force is equal to the force applied until it overcomes that force of friction and starts to move. Question 2, how do you suppose the numbers for friction in the example would change if the box were at rest on a rough wooden floor? And so again, as we think of it, like if something's rough, usually that means we're going to increase the friction. And so all the numbers would increase. It would cause the force applied to get them moving to be more because the force of friction is going up. Question 3, the force of friction can be roughly calculated for many surfaces in contact. When such a calculation is done for static friction, the result is given as F force of friction static max. What does a max mean? That has to do with, like, that's the total number of friction that the object has to overcome to start moving. So in the last one with our box and their examples there, we need 101 newtons of applied force to overcome the 100 newtons of friction, which is up here on this page. Okay. Once we've applied more than the maximum number, so once we went above 100 newtons, then we are able to actually get the box moving. And so the force of friction static max is the total number we have to overcome to actually get the box moving. Question 4, how does the amount of friction seem to depend on the normal force between the surfaces of the box and the tile floor? So again, like, we can think of the normal force as the opposite of our weight or force due to gravity. And so the more something weighs, the harder it is to push, right? If you were to push a small 45 kilogram box compared to the stacking of the two, that causes double the force, which we saw down here, it's going to cause more. So like, how is the normal force dependent on it? Well, the more weight, the more the normal force, okay, which means that there's going to be more friction according to. Okay, predict the static friction force in the example of if 3 boxes were pushed, and then predict the kinetic friction force for the 3 boxes. So again, with our static friction, we know for 1 box is above, we had to have it greater than 100 newtons. Yeah. So if we have 3 boxes, we'd have to have it greater than 300 newtons. And actually, instead of equals, we should say the static friction is greater than or equal to 300 newtons. We'd have to apply over 300 newtons to actually get this to move. Okay, for kinetic friction, it's 62.5 newtons. Again, we had 3 boxes. We're going to triple that. So we would need 187.5 newtons to keep that box moving. Yeah. That's it for the questions 1 to 5 that we're asked to do according to using these observations. Okay, I'll do question 6 as an example on the next video, and I'll probably make a couple of videos out of this. I don't want them to be too long for you.